having a critical depth xi c. And the left-hand figure indicates the experimental evidence in the very high cycle regime in rotating bending, reported by Sakai et al. And Shiwada et al. From this figure, it is found the shallow inclusion tend to cause a fatigue fracture when the applied stress is high, short life. It means that this area. Whereas in the long life low stress, the fatigue fracture occurs by inclusion distributed widely. It means that this area. Based on the above mentioned experimental result, the critical depth of the inclusion causing the cramp is given as psi less than or equal to psi c nearly equal to 250 micrometer. It means about 250 micrometer. And this left-hand figure indicates the stress distribution has a distinct steep slope across the section of the specimen in the rotating bending. And here, I would like to turn this figure vertically for the sake of better understanding of the next step. That is, and this longitudinal section is this area of specimen. May I ask you to remember this figure? And these figures indicate the effect of the inclusion depth on the stress concentration factor of semi-infinite body with a spherical cavity in tension. Alpha B indicates the stress concentration factor as the location of B nearest to the surface, whereas alpha A indicates the result as the deepest location of A. Alpha A tends to keep the value around alpha nearly equal to 2.0, regardless of the depth xi divided by rho. But alpha B tend to increase significantly according to the degrees of depth. Please remind this figure. Therefore, number 2, number 3, number 4 peak stresses at the edge of deep inclusion corresponding to the dotted line giving alpha nearly equal to 2.0. But number one peak stresses exceed the above dotted line due to the effect of the stress surface. The above left-hand figure shows a simple model representing the random distribution of inclusions inside the material projected to a common section of a bar specimen, assuming the same size of the inclusion. Here, Xi1, Xi2, Xin are indicating the inclusion depth from the smallest one for the entire inclusion. Therefore, one can obtain the one-dimensional distribution with the inclusion depth of Xi. From this assumption, the probability density function PDF of the depth Xi is given by the following expression. Equation 1. The above right-hand figure shows the PDF plotted as a function of R. In the case of rotating bending, the critical depth is given by Xi nearly equal to 250 micrometer as already has been explained in above. If the inclusion depth Xi is less than the radius rho of the inclusion as the initiation site, that is, Xi this law, the Clark initiation mode becomes the surface initiation fracture. Therefore, the probability of occurring the surface initiation fracture PS can be given as follows. PS equals this expression, equation 2. Here, in typical result of rotating bending for bearing steel in very high cycle regime, we have only 2 specimens failed in the surface initiated fracture among a lot of specimens. Total number 89. It means this is a typical duplex SN property reported by Sakai et al. And a lot of open circles here indicate surface initiated fracture. And a lot of solid marks here indicated interior initiated fracture. And 2 open circles exist in the interior initiated fracture area. Thus, the experimental probability occurring the surface initiated fracture is calculated as follows. PS equal 2.25%. On the other hand, the analytical probability of PS can be also calculated by above equation 2. Therefore, substituting the practical data are shown here. Thus, we PS equal 2.18%. The experimental result PS equal 2.25% is very closely the analytical result PS is 2.18%. Since PDF of the inclusion depth xi is given by equation 1, the cumulative distribution function CDF of xi is provided as follows. Equation 4. From the above equation 4, PC is provided as follows. This expression, equation 5. Each notation of PC, FC, and indicated here. Then, the value of xi is 250 micrometer as already explained in the slide number 1605. But we can't assume the total number of inclusions included inside the critical volume of the specimen as the present. Therefore, we provided several numbers as n and calculated the PC tentacle. And thus, we have PC value as shown here. As a result, the probability, the depth of the inclusion from the surface is deeper than xi is supposed to be sufficiently low under n greater than 10. At least one inclusion is almost necessarily located within this surface layer. In the case of interior defect, the stress index factor K is given by Murakami et al. As follows. This is equation 6. And then, the local stress the inclusion size should be substituted into sigma 0 in equation 6. If we suppose that the nominal stress having the sharpest defect of rho equals 0.005 millimeter gives the lower bound of the fatigue strength at n equal 10 to the 9th cycles, we can obtain sigma nearly equal 900 megapascal from slide number appendix 1. That is 10 to the 9th cycles, 900 megapascal. area equal pi rho square and sigma 0 nearly equal 900 megapascal, we can obtain K nearly equal 2.37 from equation 6. If the above K value gives the threshold stress intensity factor range of delta K thresholds, sigma W9 can be interpreted as the fatigue strength giving the lower bound of the distribution of the inclusion depth xi equals 0, indicated the next slide. If the inclusion is located at the depth of xi, the fatigue strength as the nominal stress as the surface is provided by sigma W9 on the ordinate. From the right-hand figure, the fatigue strength sigma W9 is given by the following equation obviously. This expression, equation 7, and xi sigma W9. Moreover, we can also calculate the upper bound of the fatigue strength at n equal 10 to the 9th cycles by substituting xi equal xi c into equation 7 as sigma W9 equal 1080 megapascal. Sigma xi c 1080 megapascal. This value is supposed to be reasonable from the statistical scatter for the experimental data point in the very high cycle regime described in slide number appendix 1. That is 900 megapascal. All specimen has run out until n equal 10 to the 9th cycle. 1000 megapascal. Some specimens have run out until n equal 10 to the 9th cycle. 1100 megapascal. All specimens have failed. From the above mentioned fact, the upper bound of the fatigue strength can be given as 1080 megapascal. From the result of the slide number appendix 1, the lower and upper bound of the fatigue strength distribution based on the distribution characteristic of the inclusions have been well explained. The PDF of the inclusion depth xi is given by this expression, and the relation between sigma W9 and xi is given by this expression. Combining these equations, we can obtain the PDF of the fatigue strength as following this equation, equation 8. The PDF of sigma W9 thus obtained depicted in the right-hand figure. The lower and upper bound are given as 900 megapascal and 1080 megapascal, as already explained above. This bound distribution and in good agreement with the distribution characteristic of experimental result in slide number appendix 1. But the probability density function by equation 8 should be defined in future. As easily suggested, there can be a lot of factors other than the inclusion depth to govern the fatigue strength distribution. Thus, this result gives only an effect of the inclusion depth. Let me summarize the conclusions. Number 1, number 2, number 3. Let me skip reading of each conclusion. For the sake of time saving. Thank you so much.